The next video in our series to review for the AP Calculus Physics test is to talk about Kirchhoff's rules. Okay, these are the loop rules and the junction and the point rule. The loop rule is just that the sum of all of the voltages in a loop are going to add up to 0. And what that means is that basically if you go around any loop in a circuit, even if it doesn't have a battery in it, and you add up all the voltages, they're going to add up to 0. Okay. And there's a couple of rules that go with that. Remember that if here's a battery, here's the plus and the minus. If you go this way across the battery in your loop direction, that's positive. But if you go this way in your loop across the battery, that's a minus. Okay. And in your loop, if your loop crosses the, let's say that you have a current. Let's say this is your circuit. Let's go back. Let's say this is your circuit here. There's your resistor. You know, with conventional current is going to go this way. Okay. So if your loop goes this way as well, if this is your loop direction, then the voltage you're going to have across it is going to be negative IR. But if your loop direction is this way, for whatever reason, maybe that's the only way you can make it, your voltage is going to be positive IR. It's negative IR because you're using up power. You're not adding energy to the circuit. Okay? But if you oppose it, you have to make it the opposite way of that. So it's going to be negative times a negative. You're going to get a positive for that answer. That's the loop rule. Okay? The point rule is just that the sum of all the currents at a point or a junction is going to equal 0. But it's an algebraic sum. So like, let's say we have a circuit like, say, this. We have a current that comes down and it's 10 amps. Then the current this way, if the current this way is 6 amps, then the current this way is 4. And I want to point out that all of those are different directions, but basically the current toward from this is going to add up to the current away from here. Okay. That they all are going to add up to the same, that the total in is going to be equal to the total out. Okay. And that's what the point rule has to do with. Basically conservation of charge. The loop rule is actually a rule of conservation of energy. The energy that came from the battery is going to be equal to the energy used up by the resistors or by whatever devices you have in your circuit. So we're going to look at two specific types of circuits. Here we have two circuits, or we have two batteries, a 24 volt and a 12 volt battery. And we have 5 resistors, a 2, a 4, a 3, a 1, and a 5. And they tell us this current here, they tell us that it's 1 amp. Okay. And they ask us what are the values of I1 and I2. And the easiest way to figure that out is actually just to make loops of them. So I'm going to make a loop of just the top, and I'm going to set a loop direction. I'm going to make it match the direction of current. So I'm going to make a loop that goes around. So I'm going to have, for the top loop, it's going to be 24 volts minus 2. I'm going to call it I1 because it's in series with that same one. There's been no breaks there. I1 minus 4 I1 minus 3 times 1 amp, they told me what that was, equals 0. So I multiply everything out. 3 times 1 is going to give me 3. 24 minus 3 is 21. So 21 minus 6 I1 equals 0. So 21 divided by 6, I get that I1 is 3.5 amps. Okay. Then I have to do the same thing to find I2 over here. So I'm going to make another loop at the bottom. I'm going to start here. And again, I'm going to make my loop direction down this way. So then I say, I'm going to start with the battery, 12 volts. I'm going to say plus 3 times 1, I times R. Notice I made a plus because my direction of my current didn't match the direction of my loop. So I had to subtract, I had to do a plus for that. Then I'm going to say minus 1 times I2, which is just going to be I2, minus 5 I2 equals 0. So I add up 12 plus 3, that's going to be 15, minus 6 I2 equals 0. So 15 divided by 6 will give me an I2 value of 2.5 amps. So there's an example of using DC, using, in this case, just really the loop rule. I didn't use the point rule much at all. I do want to point out that that I1 and I2 subtract from each other to make I3. And if you take 3.5 and you subtract 2.5, you get the 1 amp that we got there in the center. So that's good. We're going to look at another example. They give us again, it's a parallelish circuit. They give us some stuff, and they tell us that this current here, this value is 2 amps. I didn't write that on there, but they tell us that. And they want us to find all these other values. Okay. Well, the first one, they say find I1 first, then I2, then to find the value of this battery here. Well, it looks like we know almost everything in this top loop, so it's going to be easiest to do there. And I'm going to set the direction of my loop to be counterclockwise because I want to match the battery if I can. So I'm going to say 15 volts minus 7 I1 minus 5, and we know that the reading is going to be 2 amps equals 0, because that's going to bring us all the way back up to that 15 volt battery. 5 times 2 is 10. 15 minus 10 is 5. So I'm going to have 5 minus 7I equals 0. So then my value is going to be 5 divided by 7, which will be 0.71 amps. The next thing I want is I want to find I2. Well, I2, it turns out, is pretty easy because I know this value here, the value inside that is going to be I1 plus I2. I can see that they're going to add together to make 2 amps. And I just found I1. That's going to be 0.71 amps plus the current in the second one. It's going to be 2 amps. So I2 is just going to be 2 minus 0.71, which is 1.29 amps. So that's the second thing. The last thing is to come up with what is the voltage of this battery here. For that, I'm going to make a loop. And my loop this time, instead of making it counterclockwise, because I want to keep my battery positive, it's just the way I like to do it, I'm going to make my loop clockwise. So I'm going to have E minus 2 I2 minus 5 times 2 amps, I already know that, equals 0. Actually, I already know what I2 is, so it's going to be E minus 2 times 1.29 amps minus 5 times 2 amps equals 0. So this is going to be E minus 2.58 minus 10 equals 0. That's going to make the battery voltage 12.58 volts. So that's my DC circuit example 2. So you can see I was able to find all 3 of these things. I1, I was able to find I2 using that point or junction rule. I1, I only use the loop rule on. And I3, or say the battery voltage, the unknown battery voltage, I was able to find using the loop rule again. The last thing we're going to talk about is an RC circuit. Now, you can solve this, and we're going to talk a little bit about what solving it looks like. But for this one, again, I'm going to make a loop. You can see my battery symbol is kind of different than what I normally draw. I just borrowed this picture from the internet for entertainment purposes only. Okay, but for this, I'm going to have the voltage V minus IR minus, actually I'm going to erase that. I'm going to say minus the voltage of the resistor minus the voltage of the capacitor equals 0. Well, normally we know that V is going to be IR. And using what we know about capacitors, V is going to be Q equals CV, which means V is going to be Q over C. Notice I'm writing it with a small letter instead of a large capital. The reason I did that is because that's actually going to change. Like if I'm charging a capacitor, then I'm going to be putting charge onto this plate up here, positive charge, and driving positive charge off this bottom plate over there until it becomes charged. And then usually we end up doing when you derive stuff is saying V minus Q or dQ dt times R minus Q over C equals 0. And then there's a bunch of stuff to do. Like you can actually derive a differential equation, and then you take up ln and all that stuff, and you end up getting that equation that equation, what is it, a Q equals CE 1 minus e to the negative t over RC. Again, I know that you've probably seen it before, but that's a good thing to look up if you want to look for that proof of the RC circuit to come up with the charge as a function of time. But I really wanted to show you that the motivation for that is really just another Kirchhoff's law equation. That's all these things really are up here. This thing here, this thing, all these things up here. That's all we're talking about. So hopefully that helps, and hopefully you can look at some Kirchhoff's law problems and they will be solvable for you.